Okay, guys, the last video we watched, an introduction to data, talked about some ways we might go about collecting our data. In other words, we have to have an idea, an interest, or a research investigation we are trying to pursue by collecting data. We have to be clear about our population, what's going to be our sample, how are we going to collect our sample. Those are all things we discussed in Intro to Data. This section sort of focuses on what we will do with the data once we actually gather it. Okay, in other words, how do we summarize it? How do we display it? How do we look for patterns in it? That's naturally what should come next. Okay, so we're going to be focusing on numerical variables first and moving on from there. First of all, we're going to be looking at a new data set. This is UC Davis 1. So let's head over to RStudio and let's load it. And then we're going to view it. And then we want to have some help understanding it. Okay. Now, just like we talked about in class, it's going to be very important that we always have our help file open. Otherwise, we will not understand what these headings mean. Okay, they're just abbreviations right now. Having our help file open is going to help us determine what we're looking at. So it looks at, like if I'm looking at UC Davis 1, I have a survey of students at UC Davis, 173 observations, so that means 173 individuals on 12 variables. So I had 173 students, and I asked 12 pieces of information from each one of them. Okay, so we've got that open, and we've sort of got it summarized. This is 193, but I think that may be wrong. Research question. Okay, so what's our focus? Why are we looking at this data? Why will we collect it? We want to answer the research question, how many hours per week do UC Davis students spend on their computers? Now, we know that's going to be different for every student, but we're looking for a good idea, okay? Sort of a nice average understanding of how long these particular students are on their computer. Okay, so computer time, how many hours? That is a numerical variable. Okay, so we're going to begin by looking at one type of a graph. It's a graphic summary for numerical variables called a density plot. So the first thing we're going to do is we're going to learn the new R command for creating a density plot. Okay, it's actually a very simple command. Density plot, parentheses, twiddle, numerical variable that you're looking for, and then of course the data set. Now you'll see here that you have two extra little qualifiers that you haven't seen on commands before. This is really, it looks complicated, but it's not. It says main and xlab, and then you have some words over here in parentheses. Main just means the title you're going to use for the entire graph. Okay, so weekly hours on a computer. I might have added of UC Davis students, but that's okay. And on the xlab, that's just the label, what you're going to label the x-axis, so number of hours a week on the computer. So let's give this a try. You should be able to copy and paste from the slideshow. And then I can come over here and paste it in. Now, it's perfectly fine to copy and paste, particularly if you're crunched for time, but please also make sure that you have practiced typing these in. Okay, this will not get easier if you have not practiced it. And when it comes to taking exams and things like that, if you haven't practiced it, this is going to be something that's really difficult for you. Okay, so here are my weekly hours on the computer. You'll notice that you have dots here, which are the individual observations. They are the responses. So if I looked in this chart for individual 1, or this graph, there would be a dot somewhere at 10 to represent individual 1. There would be a dot down here somewhere at 5 to represent individual 2. So as you see, some of these overlap, okay? And where we have the most overlap, that's where we have our little peak, because this is measuring frequency, okay? The higher the peak, the more often we see that result in our data. if you remember from middle school math or whatnot, you know that the mode is the value that occurs most frequently. So that's kind of what this is measuring here. When we see a peak, we know we have a lot of responses at that particular value. Okay. And just like we said, our title, weekly hours in the computer, is up here for the whole graph, and number of hours each week is on the x-axis. It is not necessary to have those parts of the command. In other words, if you look here at my my console, if I were to take out the labels and the comma, this command would still work. It just wouldn't title things. It wouldn't look as nice. So if I were just doing this for my own use, that might be like a quicker way to do it. But if I were going to turn it in, or I were going to want to present it somewhere to a professor or to someone else to read, then I would definitely want a label and so forth. Okay. So when we get these results, we often use density plots to try to review the distribution of our data. In other words, when we have a big set of data, how is it spread out? Where are most of the results or the responses clumped? Okay, because those frequent results, those are important. In this particular case, we saw one peak, so we call that unimodal, one mode we tend to see here. And it also has this little bit of a tail to the right. Okay, whenever we have a right tail, we call that right skewed. Reason being, the reason this happens is you see we have two results, particularly here, that are considerably higher than all of the rest. This would be something like, think about you've got maybe straight F's in a course all semester, and then you get two really high A's at the end. Obviously, that's going to artificially inflate your average compared to what it normally would look like. That's the same thing that's going to happen here with the number of hours each week on a computer. If I were to find the average of all of these, it would probably be slightly artificially high from what most results were, because you've got these two extreme values that are going to create that kind of a situation. Okay, so we call this right skew. If that tail were on the left, we would call it left skewed, and there we would have some slightly lower values or considerably lower values. Okay, so let's try another example. This is height. Right? This is, instead of the hours they spend on a computer, this is their height. So I'm going to come over here and paste it. Okay, so here's my height plot there. Again, we see one peak, maybe the beginning of a second one there, but this is much more symmetric. Okay, now what does that mean by symmetric? If we folded it in half, we would get pretty close to mirror images on both sides. Remember that real life data isn't perfect. It's most likely never going to look perfectly symmetric, so it's okay if it's not exactly perfect, but it's much more symmetric. We don't have skew at the ends. We see that these tails are pretty balanced. Okay. Okay. So now, most often, once we create a density plot of a single numerical variable, we're going to be asked to describe it. In other words, what does it look like? Okay. So if we were to see a shape like this, unimodal, one peak, left skewed. Unimodal, right skewed. Bimodal, peak 1, peak 2, and right skewed. We see a tail. Unimodal and symmetric. Remember, it's not perfect. We often call this bell-shaped. In statistics, bell-shaped data is life. Okay, we'll figure that out as we go along. Okay, here we have bimodal symmetric. Bimodal symmetric. Okay. Now, we also want to know sometimes some numerical information about our distribution. Seeing a graphic like a density plot would help us think about how the data is clumped, how it might be spread out, but we also want some numerical associations for that. Okay, so we have an R command that will give us that information. Okay, this R command is called favstats. So let's go ahead and run favstats on computer as a variable. Again, you can copy and paste it, but you do need to be able to type it in. It is twiddle, whatever the variable is and where the data set comes from. Again, a very straightforward command. So I'm going to come down here, paste it, and hit enter. Okay, notice it doesn't return anything over here. It's going to give you your return here in the console. And what information does it give us? Okay, it gives us mean and the standard deviation. Mean, of course, is we likely think of as an average. Okay, it's one way to measure the center of a data set. The center is very important. Okay, it's one way to do that. Standard deviation we see by S. It helps us to understand how the data is spread around the mean. Okay. In fact, its literal definition is the average distance any particular data entry would be away from the mean. So if we were going to calculate this by hand, we would have to find the average. We would have to take every single value in our data set, subtract the mean from it. That's the deviations, how far away it is. Square all of those, add all of those squares up, divide by one less than the number of data values, and then take the square root. Okay? That is not a difficult calculation to do. However, it can be tedious. It can take some time, especially if you have an excessive number of data points. This is never a calculation we would prefer to do by hand. Okay, so a lot of times, this is why statistical software or using graphing calculators can be very useful. Okay. This is just a very small sample. Okay, if we had 3, 6, 10, 14, 15, and 18 in our data set, we would find the mean by adding them all up and dividing by 6, of course, which would give us a mean of 11. Here are all of the original values. Okay. And this deviation is how far away from 11 they are. Okay, 3 is 8 below 11, 6 is 5 below 11, 10 is 1 below, 14 is 3 higher, 15 is 4 higher, and 18 is 7 higher. Now, if we took these deviations and squared them, that's what this number in this category is. Okay, so we found the mean, we found how far away each one was, and we squared it. Then we would add up all of those squares and divide by 5 because that's one less than 6 values that we had. We would get 32.8 and then take the square root. So we would get a mean of 11 and an approximate standard deviation of 5.73. Okay? Again, it's not a difficult calculation. It just can take a while depending upon how many values we have in the data set. Okay? Now, here's some things to understand about standard deviation. It's always going to be 0 or bigger. Okay? It's not ever going to be negative because distance, which is what we're trying to get an idea of here, what's the average distance of a value from the mean, is not a concept that we think of in negative. Okay? So it's always going to be 0 or bigger. If it's 0, that means every single value in the data set has to be equal. That means there is no difference on average between any value in the data set and the mean. The only way that happens is if they're all the same. Okay? The larger a standard deviation you have, the more spread in a data or the more variation. Okay? For example, if I were to take a class of honor students and find their mean GPA, probably going to be clustered fairly close together. There may not be a whole lot of deviation. However, if I took the average GPA of an entire campus where you had honor students and those that were not and those that were failing, we would have a lot more variation there and thus a lot more deviation. Okay? Typical values in the data set are within one standard deviation of the mean. Okay, so if you took standard deviation and you added it to the mean and you got an answer, you subtracted it from the mean and you got an answer, most of the data that we're going to see in that data set are going to be between those two values. Okay? Typical here can be equated as approximately 2/3. So when we say that we're going to see most of those are typical values between, we mean about 2/3. Okay? For our little example we just calculated, we'd say that typical values in this set would be between 11 minus the standard deviation and 11 plus the standard deviation. Okay, so somewhere between 5.3 and 16.7. Okay, we note that 4 of the values, okay, 6, 10, 14, and 15, are in that range. So about 2/3 we're going to see fall between 1 plus and 1 minus standard deviation of the mean. Okay. So let's look at FAVE stats again. So we talked about mean standard deviation. What else does it give us? It gives us the median, which is the absolute middle value. It gives us the quartile, which is first quartile, which is the middle of the bottom half, okay? And the third quartile, which is the middle of the top half. These quartiles basically take the data and slice it up into 4 pieces, okay? You have to know the median first because you're going to cut it in half. That creates a top and bottom set. Then we cut the bottom in half. That creates our first quartile. We have a first quartile, which is from the bottom up to Q1. And then we have our second quartile, okay, which would be that percentage of the data. Once we get up to the second quartile, we've reached 50% of the data. Thinking of quarters makes this pretty logical. Okay, we think of quarters, we know they are 25 cents a piece, and we have 4 of them to create $1. Our median is the second quartile, so it's like equal to 50%, so it cuts the data in half. Okay, the first quartile is going to cut the first quarter, separate the first quarter and the second quarter. And the third quartile is going to separate the third and the fourth quarter, 75% below. Okay, we call the IQR, the interquartile range, the difference between the third and the first, so the middle 50% of the data, okay, the middle half. The median is another way of talking about the center of the data, the middle value. Okay, the IQR is a measure of spread. Okay, in the minimum value, Q1, median, Q3, and maximum, together we call the 5-number summary of a data set. Just like when we talked about mean as a measure of center, we had to talk about standard deviation as some idea of the spread. The same thing happens if we're discussing median as the center of the data. IQR is a measure of the spread of the data about the median. Okay, so we can create box plots. I'm sure you created box plots when you were in middle school or high school. Box plots are made with a 5-number summary, okay, like we just looked at. The minimum value, Q1, Q2, Q3, okay, and the maximum value of that. So if you use the box plot command, it's bwplot, twiddle, the numerical variable we're using, and where the data set comes from. Okay, if you copy and paste that and put it into R, this is what we're going to see. Okay, we're looking at this. We have here our lowest value. Okay, we also have our maximum value here. We have our Q1 and our Q3, and of course this dot here is representing our median. Notice that these 2 dots are not connected. That's because they are outliers. Most of us just think of outliers as like a really big or a really small number, but there's a math definition for an outlier. You have to be 1.5 times the IQR, larger than Q3 or smaller than Q1. Okay, so that's if you are more than an IQR and a half outside of the third quartile and the first quartile, then you are an outlier technically for the data set. Okay, so the whiskers on a box plot extend out from the first and third quartiles to the largest and smallest. Okay, and here, of course, is our definition for the outliers if we're going to determine if it really, really is an outlier or not. There's been many data sets that I looked at and I thought, this value looks odd. It could be an outlier, but it definitely doesn't mean for sure that it is until we've performed this calculation. Okay. So here's our example. We said the standard deviation was about 11.5. Okay. So if we were to perform that calculation, I'm sorry, this says standard deviation, should say interquartile range. So if the IQR is 11.5 and we multiply it by 1.5, we get 17.25. So if it is 17.25 below 6 or 17.25 above 20, that's an outlier. Obviously, someone can't spend negative hours on the computer, Okay, so we can't really get into the negative direction. But 50 and 84 are bigger, so they're flagged. Now, if you're wondering where the 6 and the 20 came from, okay, that should come back here to these values. That's Q1 is 6 and 20 is Q3. Okay, so that came from the data set there. All right, so which one do you need to do? Okay, if you're looking at a set of data, when would you use density? Okay, doing a density plot is a good and strongly recommended first step anytime you're analyzing numerical data. If the data are symmetric, that means you can talk about center very comfortably using mean and standard deviation. If you've got a skew, okay, remember what we said about means. They are highly influenced by outliers. So if we have skew there, then we're going to rely on the median and the 5-number summary, or the IQR, because median is the middle value no matter how high the high or how low the low is. Medians are not influenced by extreme values. So that's why when there's skew, we're going to rely more on this description of center than we would on the mean. Okay. Just like we said, the median is less susceptible to outliers, and so it's going to be more representative of the data overall when there is significant skew.